Let's start. So we're not quite yet starting. Hello. So good morning on our, at least on recording time in Finland. And we're having three topics today. One is something that I originally planned on looking later on. All the slides should already be in Moodle, but the first slides are on last week's section, the estimation one. So this is something we should look also a bit later on a bit more detail when we talk about Taylor series, which allows slightly more accurate estimation. But because this does happen to fit quite well on the concept of implicit differentiation with what we did last week, I thought we might want to have a look at this now. Let's wait that everyone can get settled up on the lecture hall. And now actually in this hall, I'm gonna use that whiteboard over there. So realize that this is actually mirrored compared to the other hall we're in, so I probably want to really use that one. Now also looks like everything works, so I'm using the lecture hall's own computer right now and not my own. But okay, it's 1:30, so I guess it's time we promised that we're gonna start. And let's have a look with some big promises here. Easy mathematics. So, and when I say easy, I meant that it's implicit differentiation, which was what I previously called the hardest part on the course. But actually, it's rather typical of engineers that we do a lot of work to make something easy. The upper image is how it's supposed to work. And well, okay, it's pretty small, so I can put it on both projectors. Do we lose lights? No, good. And well, okay, quite often it goes that we run into some problem when we try to figure out an easier way and then end up doing a lot more work. But hopefully, if it's generalizable solution, then for some other person, it will make things easy. So what was this implicit differentiation? Implicit derivative. Okay, so after we found out what's dy over dx, and it's some kind of a function there, we know that when x changes, in what way does the y change? And what could we use it for? Well, we might consider what is the secant and what is the tangent. So we could use this to approximate other values of the function. The first formula is the secant. So I wonder if this marker works. It does. So when we have some kind of function, and we do have here a difference in x, and over here we have a difference in y. And that, okay, I want to use a different marker than this. I have my own markers for this reason. And let's, for a moment, also stop my screen share so people on the internet will see what we're doing. I'm gonna pin my own video here, not sure if it works for everyone. And also if I'm recording my screen, not sure if it is the right way there. I need to check that still. So that is the secant, And we may remember that if we had the correct derivative here, which is the dy over dx, so the instantaneous, that would be the tangent. And however, when the change in x is small, the secant is kind of close to the tangent, and both are quite close to the actual value of the function. So we could use secant or the tangent or some combination of to estimate what might be the value of the function. Let's share the screen again. So the definition of the secant is that we have the rightmost point there, so function value of x plus some difference minus the function value at the point x is the difference in y. And if we just flip the function value on a different side there, we can see that the value of the function f in some future point should be the difference in y plus our current value. So how do we get that? When we do know the derivative, or dy over dx, we could use that as an estimate of delta y over delta x, and 10 times delta x, of course, but delta x is the amount of change we want to predict. So this is what happens then. So now we're essentially, for some reason, the slope of the secant is unknown, but we, however, can estimate the slope of the tangent, and we estimate that maybe those are the same or close enough, and we can then estimate what happens after we step forward or backward, depending on what we have calculated. And of course, we can also do things like relative changes. So if one variable at this point changes by some, then how much does the other variable change, or percentage change? So just times 100. And why should we do these kind of things? Well, one thing is, if our original values are based on simulation and it takes a lot of time, so we have a complex system that we don't really have the function for, we cannot just easily calculate the function value, but we needed to do simulations. So, and then we noticed that, okay, we have simulated a grid of points, but we do not have still the point we need. So we can then use estimation to figure out what the points roughly are around that. Or one thing is embedded electronics. This is kind of a dying breed because we're used to what we call ubiquitous computing. So computers everywhere, relatively powerful computers everywhere, or things like cloud computing. But there are applications where we need to response now, and in the device itself, we do not have that much computing power. So we'll need to do some dirty tricks. And one of those is that we use a lookup table. So we have computed values already. We have a list of values at certain points, and then based on those values, we do interpolate or estimate what the values around them might be. So much less computing power if we have beforehand done some work to get intermediate results. And of course, in some cases, we still have handbooks and tables that we have values for some of our problems, but we do not have values for all of them. And the last one, our homework today does actually say that estimate the value. So you're supposed to use this theory there. We'll have a look at that on exercise as well. And I do also have 3 o'clock, well, 2 to 3 today office hours. So those of you who cannot come to exercises, have an option. And I also have office hours 2 o'clock on Friday and Monday. On an example of how to do application. So now if we have a difference in area compared and how it depends on difference in radius on a pipe. This is, by the way, straight from 141, example 1 on that page. So it should be the delta big A over delta R times delta R. And we replace the second with the tangent, so dA over dr. And that's 2 pi r times delta r. Okay, relative change, so we had that. And now 1.02 relative change is same as 2% increase. So we plop that into the formula. Okay, after simplifying, so 1 pi r goes away. After we substitute that delta r is something times r. And it gives us 4%. And this is not accurate. Okay, this is really simple. So in this, we could have used the pi r squared formula, which tells us that that the increase is r squared, and if r moves by 102, then 102 squared is 10404. So we get 4.04% increase in the real value, but it's relatively close when we estimated 4%. Okay, and that's the easiest part of how to estimate things. So we have pre-calculated some points and some tangents, which is the differential. And now we can use these points to estimate that maybe the intermediate points are somewhere here. And if what I draw just on the board is our, where's my mouse? There it is. Our example, we can see that in some cases, we may notice that if we cast from different data points, we might not have some slight difference here. So our data points are here. The solid lines are standing for the tangents. So depending on where we cast, we might have some kind of a variation. There will be error. We'll have a look at the error formulas a bit later on. And of course, you could then do some kind of interpolation instead, that if you're moving between these points and you know the slopes, then you would correct by trusting more on the estimation that's from the point that closer. But that's still slightly more advanced topic. We're going to go through that a little bit later when we talk more about estimation. So for now, we're assuming that we're really close to one of the known points with a known tangent, so known derivative, and thus we can just use that point's value for estimating other function values down near that point. Okay, let's see for more.
Can you go back to the previous one?
Yeah, I hope. There we go.
In the relative change,
Yeah, there's something funny.
yeah.
Yeah, it's missing one R
Yeah.
because we can see that we estimated that delta A is 2 pi R delta R. So it's just a typo. It's missing one R from the numerator. So where's the mouse again? So over here we can see that this should be 2 pi R delta R, and I've missed one R here. Then it makes sense. And next one. Okay, so might have been useful slightly earlier, but we're talking about integration as well. So exponentials, logarithms, something you should be familiar from high school already. One of those topics. Okay, this is just the first one of these. But actually, logarithms used to be used a lot in engineering. And heat dissipation usually produces into models. It does produce exponential solutions, but just taking more logarithms of that probably isn't going to solve the engineering problem. So one of the most useful property is that if we take the logarithm of two numbers in the same base, we can then with the logarithm of a multiplication of two numbers, we can move that into addition. And similarly, if we have something that's a power of something, then that becomes multiplication. So we kind of with a logarithm, we take one step down from so powers become multiplication, and multiplication becomes addition. And this log k means that the base is some number k. Usually we tend to use natural logarithms simply because those are having most likely to ready-made functions in our computing systems. An exponential is an inverse of logarithm. So if we have some a-based logarithm of x, that means that x is a to the x for some base a that is greater than 0 and not 1, because 1 to the power of anything tends to be usually 1. And a to the power of x, so x can be in real numbers, but the range is from, it doesn't go to 0, it doesn't go to infinity. And then for the logarithm, the x needs to be from 0 to infinity, so it cannot be negative, and it will return all values. And I already spoiled that, but when we have the unity, a equals 1, then we're having powers of 1, so it kind of just stays in the 1 point. And then what's the difference of a power and an exponential? So if we have an exponential, we have some base a, and then our variable is in the exponent. If we have a power function, then our variable is the base, and we're having some fixed power a. And what you maybe have used on school is that we have two constants. So some constant base to some constant even integer valued power. and multiply n times, but this can be expanded to all kind of rational numbers and even real numbers. So we may have whatever, well, a of course being real and also real powers. But when you usually see this n, then it typically means that it's some natural number. So it's 0, 1, 2, and so on. Okay, natural logarithm and exponential totes have the nice properties. So the definition of the natural logarithm is this, and this is the area of the given integral from 1 to x. And when we're having x between 0 and 1, it's negative, and when x is greater than 1, it's positive. So it got the natural logarithm has the connection to the inverse of t, and this easily gives us a derivative. So by definition, when we have the integral as a definition of natural logarithm, when we differentiate it, we get plopped out 1 over x as the derivative of the natural logarithm. And similarly, if we have the integral of 1 over x, this is the reason why we get natural logarithms out of it. So again, by the definition of natural logarithm. But for logarithms, x must not be negative, so we take the absolute value of x. And then the inverse function of that is the natural exponential, which we commonly in computer systems write exp of x, but also very common shorthand of e over x, where e is I pretty commonly say Nepe's number. That's what we say in Finnish, but it's named after John Napier. I'm not completely sure if I pronounced that in a slightly French way because he was an Englishman. And E is a transcendental number, and this has an interesting property of being its own derivative, and almost its own integral, but then remember the plus c. But in many applications where you integrate also something else, you can almost deal it like its own integral, because you'll get it, or its own antiderivative, because you get the plus c anyway. General exponentials, we can add also to inverses there. So if this comes in handy if you need to differentiate those. So a to the power of x is same as e to the x times natural logarithm of a. So we take the what do we have here is we get e ln a to the power of x, but when we have powers of powers, that's the same as multiples of powers, so we can draw it over there. And this is how we can find the derivative there. So derivative of a over x. So we first expand to the exponential form and then apply chain rule. And then let's get back from that part. So expand. So can reverse expansion, and we get that the derivative of a power function is well itself times the natural logarithm of the base. And similarly for the logarithm, we should do the opposite one of that, and we end up having 1 over x ln a. And if you ever need to work about volumes or, well, sign law strength, you have decibels, which are actually on the power of 10 scale. But whatever logarithm we have, we can divide now whatever base we have. So this works in any base, not only in the natural base. So so if we take the base a logarithm of x, that's the same as any base logarithm of x divided by any base logarithm of a, where in the quotient the bases must be the same. But because usually we have, so what this actually means is we usually use the natural logarithm because our computers do have the functions for natural logarithms. But what that actually means is that if we have log base a of x, that is log sum b of x divided by log also b based of a. So we have a peek on the board. So we go this. So the base goes downstairs and the parameter goes upstairs. And this b, well, it may be the same as a, but it can get a bit kind of what's the point thing there. And anyway, because logarithm of a base logarithm of a is 1 anyway. No, I still need to get back. Okay, and then why we didn't have this earlier, this is we can do differentiation if we have whatever function f, but the function f is now on the power of some other function g. And general rules don't work, but if we use the earlier rule for expanding functions to exponentials, the same power rule that works for other numbers works also for functions. And okay, we have that. We could use product rule and also chain rule, but chain rule gets really simple when our external function is e to the power of x. And now we could figure out what our derivative is. So let's see that y is x over x. So our rule here is that if we have f to the power of g dx, this is supposed to be an x, then we can expand that to d dx e g ln f. And now we had f equals g e equals x, which is the simplest case. So we have what we wanted to differentiate was dx x to the power of x, which we usually don't have a rule for, but now we know that it's the same as ddx e x, natural logarithm of x. Okay, so our external function is e to the power of x. So when we apply chain rule, we get derivative of the external function, which is still ex. Its parameter is the internal function, which is still x ln x times the derivative of the internal function. Now this requires multiplication, so we get derivative of x, which is 1 times ln x. So 1 times ln x is ln x plus x, and then the derivative of ln x, which was, in memory, did we have it on the material? 1 over x. Okay. And this has a nice property here. And for x, other x that is not 0, these cancel out. So we get, in this case, with the function being this simple, we get ln x e to x ln x. Yeah, okay, good point. Don't entirely cancel, but there needs to be +1. So that way. And actually we can, no, we can't further about this. I would probably take as is. You could then note that this ln x e to the power of x ln x plus ex ln x. So might be tidier, depends on what we're going to use that for. So if you're gonna,
Sir, I'm sorry. Can I ask a question?
do ask.
Yes. So you said a particular like case when a logarithm of the base of a equals to 1.
Yeah.
Okay. So is it true for a that has the values between 0 and plus infinity, or is it true for every single value of a?
So the question was that we end up staying on one point if we have a base of 1. So the problem here is that logarithm of 1x does match so we're doing something from the definition of logarithm. We have 1 to the power of x, which ends up being always 1. So
yes, okay, but what if we say like logarithm of base of x, like not 1 of x?
Okay,
but
that's something that. So then we would be doing. I haven't run into that kind of function, so that's actually an interesting one. So we would essentially be thinking about what we just had there. I'll need to find out. So don't remember running into those kind of problems. But now we're having changing base logarithms. This does sound pretty interesting though, in the matter of it being complex, but I'll need to check. This is not something I'm willing to discuss. Well, it's already 9 o'clock, but I haven't slept too well, so I'll need to find out that what happens with x-based logarithms. Technically, we could probably just change bases here, so we could get into, yeah, it would go to ln x over ln x. So that should also always result to 1 as long as x is greater than 0.
Yes, so basically that was my question. So
Yeah.
x needs to be greater than 0. It can't
Yeah.
be negative.
Yeah, because yeah, a needs to be greater than 0, and of course in this case the logarithm value cannot be 0 either. So because otherwise we get a divide by 0. Yeah.
Okay, thank you.
And that's essentially the simple part of logarithms. Okay, then let's go to inverses. So one example of inverse functions is this, that if we have a logarithm of x, then the inverse is a to the power of x. If we're following on the textbook, we should be going to chapter 3 now. So if I remember right, chapter 1 is the basics. Chapter 2 is chapter 1 would be, actually chapter 1 might be some of the basics already, and it's a kind of chapter P, which is the preliminaries. But anyway, new chapter for those who are using the textbook. This is on the edition that's in the library, that's 175. So this is something that we also already used in the exercises. So how to find the inverse when we solve an equation. There are some tricks that we can use for inverses when we differentiate. So function is 1-to-1 if for all possible combinations of x's where the x's are not the same, then the function value is not the same. So this means that it maps a relationship between two functions, y and x, such that all combinations are unique. For example, if we have the simplest part is y equals x, so then all values of x map into a separate y. If we look at y equals x squared, so I'm now going to draw in a different color. Where's there's the mouse again. Okay, I'm actually not sharing the screen after the previous board part, so what I was showing there. So yeah, so essentially if we have log x of x, we can do the expansion, and then we'll end up having some base of x divided by the same sum base of x. And tend to inverse functions. But actually now what I was looking for is stopping the screen share. And so what we now have on the board is one function that does have a clearly defined inverse function. But if we consider y equals x squared, then we would have x equals plus minus square root of y. And now we can see that for some y, we have two x values. And yeah, for being invertible, then of course it's the other way as well. So if we had plus minus square root of x, then it has a vertical line that intersects it more than once. Yeah, but that's its definition of function. So the question is, if we invert the function, is that also a function? If it is, we have a one-on-one function. Another piece of knowledge is that if we have one-on-one function and we have equal function values, then we must have equal parameters. Okay, so so if we have such a one-on-one function, we can then solve that. And do note, we mark the inverse of a function with a superscript of -1. But if we have the reciprocal, which is a function to the power of -1, that is the reciprocal of the function. So in Finnish we would say käänteisfunktio for the inverse of function, and then function käänteisluku for the reciprocal. Then we mark it like that. Also -1. That's kind of a really easy to get confused if you have both in the same problem. So yeah, if we can mirror it, then we get the inverse. If both are functions, then it's invertible. Is x to the power of 3 invertible? It's an odd function. That is, it's not strange, but it is an odd function. We have x to the power of 3, and we can draw some axis of symmetry here, and then on that axis of symmetry we can invert it. We're also having this that it does have unique values, so yeah, it should be invertible. So yeah, all monotonically increasing and monotonically decreasing functions are inversible. If it's continuous and derivative of a function doesn't have a real root, it's inversible. So that's one way to check if you can differentiate it. And the derivative does not have a real valued root, we can invert it. This means that the derivative must be okay. There it might, yeah. And of course, if there's jumps in the derivative, then yeah, that is the possible so the derivative actually needs to be continuous as well, not just a function. Otherwise this description would match the absolute value function, but the absolute value function, so which looks like a sharp B, it does not have a derivative at 0. And occasionally we do have some inversible functions which are not continuous. Equivalences, so I may have used those lines somewhere. So formally, if we have this kind of a double arrow, arrows and lines, double arrow to the right, it tells that it essentially it reads therefore. So we have something, therefore we can deduce something else. But if we have this double-headed arrow, double arrow, then this means that these two things are exactly the same thing in every way. So the difference from equal sign is that they have the same value, and equivalency is even stronger. So essentially that means that they must be exactly the same thing. And occasionally we get inverses of inverses and get the function itself, which can be useful for solving things if we can input something in the middle and then make the mathematics easier. And an identity function is such a function that returns itself. Okay, is that function inversible? Any guesses? Anyone remotely? Is it a monotonically increasing or decreasing function? Let's see. So we're having, this should be easy to follow even if you do not see the camera. So we have y equals 2x minus 1. Y dash, so the derivative is derivative of 2x is 2. Derivative of minus 1 is nothing. So we have derivative of 2, which is always larger than 0. So this is monotonically increasing. And therefore, this function is inversible. Okay, so what's the inverse? So let's solve this for x. So this is really simple explanation. Simple function to do this. So we have 2x minus 1. Both sides. So this large bar, I'm drawing on the board a long bar, which means or I guess it should be 2 bars. So we're doing the same thing both sides. So plus 1. So y plus 1 equals 2x. Divide both sides by 2 or multiply by half. So we get y plus 1 divided by 2 is x. So f, so x equals the inverse of f with parameter y is y plus 1 over 2. So essentially we know how something behaves, and now when we need to find value of something, same thing you had on the first exercises, then we will invert the function and see what the inverse is. Okay, if we do not have an invertible function, what do we do? What if it's not one-on-one? Then we need to check that on what domain. So if it's not globally invertible, then we might have a subdomain where it's still monotonically increasing, and we can invert it within that part. And yeah, we do occasionally have some functions which are its own inverses. Or yes, in the same way you just swap the parameters and all the variables around. And yes,
so that one is going to be just symmetrical to the original function.
Yeah.
And for example, y equals x, it's the same function with its inverse.
Yeah.
All right.
In statistics, you will call depending on which one is the variable you can change, and we call controlled variable and dependent variable, but those are both variables still there. Derivatives. So if we have an invertible function and we know the function, I want to find the derivative of the inverse. Then if we have an invertible function, then we have a differentiable inverse always. Should work something like this. So if now we're kind of doing implicit differentiation as well. So dy over dx should show up like this. So dy over dx is 1 over f dash y. So we're now differentiating the inverse function. And now for the y, we're inputting the inverse. And also on the right side of it, for the dy, the dy stands for the differential inverse. So the differential inverse for x should end up with this kind of a formula. So the reciprocal of the differential of the function with the inverse function as a parameter is the differential of the inverse function. And that's today's theory dump. Quite a lot of theory in a small amount of time, and it's morning. Yes, I know. Just for some extra pain, well, I don't just want to hurt people, but let's have a look at what we're doing on today's and tomorrow's exercises. You have these are due midnight next Wednesday because you're getting this late. So you have a bit more time to ask questions. So we have that kind of function. Sigmoid looks like a slightly wide S. And here we can see that actually this C plus 6 suggests that it has been shifted. So my first hint would be that just shift it back. So it is from -6 to +6. Since sigmoid is zero-centric, and it gets a lot easier to differentiate. And then you first need to use the quotient rule. And then we get some kind of multiples there. But after second use of the quotient rule, and I haven't, for that kind of a problem, I really don't see the use of putting up the solution, but do have intermediate steps, and you can, if in doubt, you can input this into Wolfram Alpha or some other CAS system. It will solve it for you, essentially, at least show the final solution. In Wolfram Alpha, so the intermediate steps is a for pay feature. And one thing, of course, you can right away put that 5 out of the differential mark, so 5 times differential of 1 over 1 plus e to the power of minus t. So it is 1 over 1 plus e to the power of minus t is the sigmoid function. There are a few different equivalent ways of writing this. So for example, e to the power of t divided by 1 plus e to the power of t is also, but that, in my opinion, is harder to differentiate. So, and then we had one example on implicit differentiation. It was that thermodynamics one. So if we have pressure and volume, and we're having small changes in volume, how does the pressure change? So that's one example we use implicit differentiation for. And one something that usually for engineering management people, but what's useful to understand for all engineers is supply and demand. So typically we get these kind of cross effects when we try to model supply and demand. So if P is the price and Q is the quantity of products sold, we're getting something like that shape of, okay, the constants there, the 2 and 2s and 200s and minus 1, those are, well, whatever. So these are not real, but typically you would expect to see functions of similar shape when you're thinking about supply and demand. And we can calculate several things. So one is the marginal price. So how much does the price change if we try to sell a different amount of products? So that's minus dp over dq. Or then we have what we're going to calculate here. How does the assumed number of sales and therefore amount of revenue change if we hike the price? And the interpretation of this, because we don't get integer solutions there for the number of products sold, depends on how you deal with rounding. So you may need to consider this, and so this has a little bit of verbal explanation expected out of this problem. And finally, antiderivative. We remember that force is mass times acceleration. If we have that kind of an impulse, what does the location function look like? So just integrate it twice. And that's our following weeks of, well, this week's exercises, but the return date is next Wednesday. Some of these so none of these are difficult, but you need to be careful in applying the integration rules. So on the lines of, don't do what I did last lecture. I tried to do it in my head without having a look at formulas. If I had written the formula, I would have probably noted that the power goes, we need the reciprocal of the power. So the example we had last formula is this. And do note, if you use Wolfram Alpha to check on these things, remember to use all the parentheses. So otherwise powers get calculated first, then division, and so on. So when you have a specific order, you want to have things calculated, put all the parentheses in when you're using computers. Computers calculate exactly what you're typing then, and not necessarily exactly what you wanted them to calculate. Okay. I haven't yet had my morning coffee, so I guess it's about time. And any questions, then do ask. If not, time to